Hi everyone, welcome to this video on lesson 6 of the atomic structure and periodic table scheme of work. This lesson is obviously really important in that isotopes are something that comes up quite a bit later on, actually as much in physics as in chemistry when we do the radioactivity unit. But as well as being a chance to introduce that new concept, really what I think this lesson is all about is just having another opportunity to practice what we did in the previous lesson, which is just using the nuclide notation to work out how many protons, neutrons and electrons there are in a given atom. So in this lesson I tend to start with some what I think are relatively concrete and familiar materials. So we might take a lump of coal like this, which I'm just going to draw very roughly as follows. So there's a lump of coal. We could draw a diamond. A little kind of sparkle here. My drawings of diamonds are not the best, but hopefully that's clear. And we could even draw a pencil, or I mean, I'm not sure drawing a pencil is necessarily a worthwhile thing, but anyway, we could draw a pencil like that and say the graphite inside a pencil is also made of carbon. And what you wanted to say to students is that actually if you were to zoom in on all of these materials, they would all contain mostly, I mean obviously in coal there's various other atoms as well, but they would mostly contain carbon atoms. So if we were to zoom in on any of these, so if I just zoom in like this, and we could do the same from diamond or graphite as well, what we would see is a carbon atom. And this is just, like I say, a really good chance to say, well look, the carbon atoms that we get inside most materials that are made of carbon are what we call carbon-12. So one thing that we are introducing here, and again maybe I'm biased as a physicist because I think this is kind of more important for physics, this notation, but it's really helpful that students have this. I'm going to introduce this notation and say, when I do this notation, I'm going to make this explicit to students. When I do this notation, what I'm showing is carbon followed by the mass number of this particular atom. And this is really important because we're going to introduce relative atomic mass in the next lesson. When we're talking about mass number, we're talking about particular atoms. And what I want to do next is turn this notation, name dash mass number, into the nuclide notation that we introduced last time. So in this case, I know the mass number is 12, it's carbon, so I'm going to do it like that. And this is where I actually, I don't have a periodic table to hand, but you should always in this unit have a periodic table to hand. If they need to find the atomic number of carbon, well, they can go back to their periodic table and they will find that it is 6, okay? So what we can do next is, if I just move down a bit, we can do our PNE, protons, neutrons and electrons. So I can say, well, okay, atomic number tells me protons and electrons straight away, so I can write those in without even thinking. And then I know that my total number of protons and neutrons is equal to the mass number. So those two taken together equals 12. So that means I must have 6 neutrons as well. And what you can do then is say, well, okay, inside my carbon-12 atom, what I've got is my tiny nucleus in here. I've got my electron shells. You can draw it as we would draw it for GCSE in terms of when you're drawing the electrons. So I'm going to draw 2 on my first shell. And again, students don't need to worry too much about this at this stage, but you can say you would actually have 2 shells here, and there'd be 2 in the first and 4 in the second, and that's fine. And if we were to zoom in on this nucleus, well, what would it look like? Again, remember, we want to always have this kind of mental model and map that back to, give them the mental model here and then show how that maps onto the more abstract representation. So if I then draw my nucleus, I've zoomed in on my nucleus here, and make it explicit what you're doing there. So I'm looking now on a very tiny scale at the nucleus. Well, what carbon-12 has, because of this notation, that means it must have 1, 2, 3, 4, 5, 6, and then 1, 2, 3, I've got 6 neutrons as well, 4, 5, 6. And I can even label these just to make it really, really explicit. And you can tell students that most of the carbon that you find in the universe looks like this. If you were to zoom in on this submicroscopic, subatomic level, and you could actually see inside the nucleus, you would see all of these subatomic particles held together. And again, if they ask you, why are they held together? Well, why do they not push apart? Because of the same charges. You can talk about the strong nuclear force if you wish, but for now, just tell them to believe you. Anyway, so this is the most common one, and what we've done here is mapped this kind of slightly more visualizable model to the abstract symbolism. But what we want to tell them is, and again, it's worth looking up some of the stuff about carbon dating and how scientists can date, kind of work out the ages of very ancient fossils and things like that, using carbon-13, which we're going to look at next, and carbon-14, I think. I would have to check that. But anyway, let's draw a kind of fossilized fish or something like this. So we can draw some bones like this with a kind of skull there like that, and say that in some of these ancient fossils found in rocks, so I'll draw a fossil in a rock there, if you were to zoom in on here, what you would actually find is something that can be slightly different. So let's draw this atom, and first I'm going to go through the same process. So first I'm going to say you actually find another type of carbon atom, and this has, when we use this notation, it's carbon-13. What does that mean? Well, this is the mass number, so I'm going to go 13 here. I know that it's carbon, so it's going to have a capital C, and it's the same atomic number, and this is a really good opportunity to stress that any atom that has the same atomic number, i.e. the same number of protons, must always be of the same element. So this is where you're not just practicing doing this again and relating it to this picture. This is where you're really introducing the idea of isotopes, to say if they have the same number of protons in the atom, that must be an atom, they must be atoms of the same element. But what you can say here is, look, this one, which we've discovered, and again, scientists made measurements to measure the mass of various atoms, this one has a different mass. Why? Well, let's do PNE again. So we've got 6, I'm going to put 6, 6. I'm going to be doing this in pretty much every lesson in this scheme of work, because I really want to build students' ideas up from first principles, always coming back to this kind of core idea to do with the Bohr model. So I know that the mass is 13, and therefore my number of neutrons is 7. So what does this atom look like? Well, I've still got the 6 electrons. There's my nucleus. I'll zoom in on that in a minute. I've still got the 6 electrons. So those electrons I'm just going to put in the shells as I did before. Again, don't worry too much about the electrons. We're going to come to those in a couple of lessons' time. But if I zoom in on the nucleus here, what does it look like? And you can show them how different isotopes of the same element look different. Well, in this case, I've still got 6 protons, so I'm still going to draw my 6 red circles to represent the protons. But this time, I've now got 7 neutrons. So I'm giving them a mental model of what these different isotopes look like. 1, 2, 3, 4, 5, 6, 7. And again, I'm going to label these up so they can see that these look very similar. They've got the same number of protons, they've got the same number of electrons. But these two things, these two kind of flavors, let's say, we sound like particle physicists there, but anyway, these two different flavors, species, whatever you want to call them, of carbon atoms, they have the exact same number of protons, but they have different numbers of neutrons. And then you can finally come back to the title of this lesson and say carbon-12 and carbon-13 are what we call different isotopes of the same element. Now, I can pretty much guarantee you that most of your class is going to go through this and go, what on earth are you talking about? That's absolutely fine. We are not expecting students to really master the concept of isotopes immediately. That's something that's going to come over many, many years. So it's just worth emphasizing. It's really important that we introduce the concept and we explain it as clearly as we can. We could also do some further examples. So, you know, we could do examples like hydrogen and deuterium and tritium that are found in the sun. But again, they'll come back to these ideas again and again as they study nuclear physics and radioactivity and so on. So it's not that we, you know, need every single student to understand isotopes straight away. It's important that we introduce the concept to them, but we're going to keep coming back to it. What is helpful is that they go through and they practice this method of moving from their mental model of what it looks like inside atoms to the way we represent that using the numbers and so on. And what you'll see is the deliberate practice in this lesson is actually just for different isotopes of the same element, noticing that there can be different numbers of neutrons even though there's the same number of protons. But it's just practicing these same methods again and again and again. So I hope that's clear what this lesson is trying to achieve. We'll build on this idea of isotopes and look at relative atomic mass in the next lesson and in the next video.